Let's see what happens. All right. I have balance issues today. Let's just try something here. If I gave you an equation that looks a little bit strange, but it's just a little bit out of whack in a way. What's the one thing that's kind of like not quite right about this? Yeah, so what could I do to make it look more normal? What is this trying to be? This is trying to be a circle, but it doesn't look like a circle equation. So what could I do? Multiply by 9. And then it would become x squared plus y squared plus 9, no problem, right? No problem. You guys with me? Okay, now, let me just look at it in this form, though, because this ends up being a more useful form for ellipses. We'll see why. What's the biggest x can be? That's a really weird question, but think about if you try to make x like 4, right? Then you get 16 over 9. That's bigger than 1, isn't it? Okay, so far so good. Which means this piece would have to be negative. So you can subtract from 16 over 9 and make it become 1. Can this piece be negative? No, because thankfully we're not graphing over the complex numbers. Oh my God, that would be crazy. We're not going to do that. So the biggest x could possibly be is when this piece equals 1, and that's when x is 3. And then the smallest x could be is negative 3. I like it, you guys, because then you get the same thing. You get 1. So same thing with a y, though, right? So this is sort of like what it's trying to say to you about when the numbers are equal, you'll get a circle because it's allowed to go out equally far in both directions. So this will just be a circle of radius 3. If you bring the 9 over, it's more in standard form for a circle. But when I'm dealing with an ellipse, so all I got to do to make an ellipse is this. That's an ellipse. That's standard form of an ellipse. X squared over something plus y squared over something equals 1. Because now I can see how far will this be able to go out on the x. The same idea as before. How far up and down on the x can this go? You guys can do it. Same thing as it was. Why this equals 1 was as far as it can go. If it went over 1, this guy can't be negative to bring him back down to 1. Same idea. So that x can go from negative 3 to 3. I like it. And what can y do?
4.
Yeah. From negative 4 to 4. So now you can see that's going to make an ellipse, isn't it? So then you'll get...
Yeah.
I know this looks a lot like the circles I was making earlier, but I won't. Still, it's an ellipse because it's longer this way than it is that way, and I really hope you can see. And again, I try to teach a lot of things in the way that I wish I had been taught them, and nobody just ever just pointed it out like that. You can see why these numbers relate to how far they go in that direction. Why did I start at the 0, 0? Why is 0, 0 the center? What would it look like if 0, 0 wasn't the center?
Like negative on the outside or positive?
Not on the outside. It would actually be... So if I wanted a center to be at 2, 1, I would have to make this x minus 2 squared. See, that would move it over 2 plus y minus 1 squared. Same shape, just over 2, up 1. And see, we got to get really used to this. This is how I move around. Remember what I told you when it's with the letter, it's the opposite? So with the circle and an ellipse, everything's kind of with the letter. So x squared, y squared. So you can see that is 2, 1, because it's the opposite when that number's with the letter. Okay, hopeful. So the standard way of breaking an ellipse down then, you're given an equation. So if I give you this equation, x squared over 4 plus y squared over 25 equals 1. Now you see how you don't, I give you on the handout the textbook way of breaking down an ellipse. But it's kind of silly when you realize the idea behind it. How far am I going to go out on the x-axis?
4.
2, right? So officially we would say a squared is 4, so a is 2. So x squared over a squared, y squared over b squared. B squared is 25, so b is 5. So I'm going to go 2 out on the x-axis, 5 out on the y-axis. That's definitely going to be one of these kind of freaky little UFO things, right? Otherwise known as ellipses. What else? Oh, and then there's something really interesting. This is kind of getting to what I was saying earlier. We're actually going to be able to calculate the foci, the focus, each focus. Right? It's not focus, it's good old foci. So A is 2 on the x-axis, I go out 2. B is 5, I go out 5 on the y-axis. And then here it is. So I'm done with the graph of it. Now I am. Cool. But now I want to figure out where the foci are. So really, the definition of an ellipse, I'm trying to save you from the derivation of it. I tried to just kind of show you why this makes sense. I change those numbers, make them not the same, and then it's going to be an ellipse. But the definition of an ellipse, they have a picture of it. Where do they have that? Oh, there it is. On the top of page 880. It's basically the idea of if I put 2 tacks down and put a string loosely between them, and I put a pen in here, and I kind of go around it as much as the string will let me do it, I'll trace out the shape of an ellipse. So if I put the foci this way instead, it will be one of these kind of ellipses. If I put them closer together, it'll be a different shape. It'll be more circular. Because think about a circle really is where the 2 foci merge, right? And then that's the center. So an ellipse is just a circle that has more than one center in a way. It's really kind of freaky. Okay. Oh, so how do I find the foci? Well, here it is. It's kind of interesting. It's the opposite sort of the Pythagorean theorem. Because where will each focus be? Will it be inside or outside? It's sort of a weird question, but will it be inside or outside of the shape? It'll be inside. So we rotate around the sun, and the sun is at a focus. So we go around the sun. The foci are always going to be inside, like the center is inside the circle. So that's why it kind of makes sense that the position of the foci is going to be, in this case, I think the book always does it a certain way. In this case, it'll be b squared minus a squared. So it feels a lot like Pythagorean theorem, but it's a minus. So I always remember it's a minus because I want it to be inside. For a hyperbola that's going to turn this way, it's going to be outside of the center. It's going to be out there, right? Pretty much it's always, if somebody threw a ball at me, what am I going to do? I'm going to go, right? I'm going to make this shape with my butt, So it's like the focus is here. Now if I push it out further, it's going to go, And the more closer to the center I'm going to get, it's going to be like, oh, okay. I don't know, does that make any sense at all? I mean, that's my own interpretation. So what's it going to be here? It's going to be c squared equals 25 minus 4. So c squared equals 21. So c is the square root of 21, whatever the hell that is, somewhere between 4 and 5. And see so somewhere between 4 and 5 is going to be the focus. Somebody help me out. What is the square root of 21 exactly? 4.58. So like 4.6. So one focus will be right here. I always put a little x for the focus. 4.58 and negative 4.58. There are the 2 foci. So if I drag them in, this would become less elliptical, become more circular. Until I merge them in the middle, and then that's a circle. Let me stop there for a second. How are we doing there? All right. Okay. Semi-decent. So here's kind of what's interesting about hyperbolas. Remember how we said earlier that it was related to... So here's an ellipse. Here would be the associated hyperbola. It just opens outwards, right? So I'm going to do a hyperbola based on this equation. I'm going to change the one thing that I need to change to make it become a hyperbola. let me look at this just number-wise. If I said x squared plus y squared equals, it doesn't matter, 16. This is closed. What do I mean by that? Neither letter can just get as big as they want to be. Do you guys see that? Can y be 7? No, because I'm not using complex numbers. There's no squared real number that is negative. If y is 7, that's 49. How do I get it to 16 if I'm adding a positive number? I can't. So it's contained. So that's why the plus actually results in circle or ellipse contained. If I want to make it not contained, where the variables can get as big as they freaking want to, I got to put a minus here. If I put x squared minus y squared, now they can each get as big as they really want to. If x is 7, that's 49, y can be whatever minus that is 16. Do you guys follow? All right, so if I made x 7, can you figure out what y's got to be? Well, yeah, subtract 16, take the square root, you'll get a number. Not a beautiful number, but it's still a number. It's still possible. It's not an imaginary number, it's a real number. So putting a minus in the middle makes it not contained, makes it a hyperbola. It actually just opens out instead of being contained. So if I do the hyperbola equation related to this, let's see how it relates to that. So if I do this one here, now that I put a minus there, now let's first talk about which way is it going to open. So a hyperbola can either be like this, or it could be like that. So it could open like this, or it could open like that, right? Which variable up there has intercepts? So if I put a 0 in for x, do I get any y intercepts? You can, come on, you can do it. Think about it. Can I make negative y squared over 25 equal positive 1? No. So there's no y intercepts. But there are x intercepts. Make y 0, I get x squared equals 4, I get x is plus or minus 2. There are x intercepts. So whichever variable is the positive piece, the x squared or the y squared, that's the axis that it's going to sit on. So in this case, since x is positive, the x squared, it's going to go like this. It's going to sit on the x-axis. If this would have been turned around, it would have done like this. I don't know if I could do that at the same time. Yeah. Okay, right? It's like doing this. Okay. Now watch this. This is kind of nifty. The hyperbola is probably the hardest one because it's got the most kind of moving parts to it. But they all kind of work together to help you graph this thing. Aw. What is wrong with you? You poor little dude. This whole thing's going to be out of focus. Oh, okay. So here's what you do. So it's going to, in a way, it's going to be the opposite of this. So it's going to basically be like this, but I need a guide to help me draw it correctly. I mean, does it go like this or does it go like that? I have no idea. So the beautiful thing is, here's the way this works. You still, how far is it going to go on the x? 2. Still 2 and 5, right? Except here's where there really is a point. There's a point at 2 and negative 2 because it's on the x-axis. It's allowed to have real x-intercepts. Can't be on the y-axis. It's going to turn away from the y-axis, right? But there still is something about this. Here's where things get interesting. If I draw the rectangle up there that kind of defines a rectangle. See how the ellipse would be contained inside that rectangle. Cool? Yes? You guys see that? I can just pick this up and it goes. It would be contained inside. The hyperbola is kind of like balanced on the outside. And what helps me figure out how wide it is, how quickly it gets wide, is I can draw through the corners. I draw asymptotes. Oh, shit. So now I know it gets wide pretty quickly. Wee-haw. So roughly like that. You could also plug some points in and see what you get. You're going to get something semi-gross, but still it gives you an anchor point to kind of graph. But those asymptotes help you see how wide it gets. Now, so what if it would have been, instead, if it would have been y squared over 25 minus x squared over 4 equals 1, I would have done all the same work, except it would have been here, right? Why would it be there? Because now it's allowed to have y-intercepts, not x. I like it, I like it, I like it. Because I could cut this ellipse like this and let it open that way, which is this thing we did. Or I can cut it here and let it open out, which is the second thing, the black dotted line. Now, am I cutting in mathematics? No, I'm just saying this is the visual of what's kind of happening. That's the connection between the two. All right.
So you can just mirror both sides? So you can
Yes.
cut it in half and just flip it in half so you go two more over.
Yeah, it gets a little, so you can imagine this curvature here is the same as the curvature here.
So you go two more.
But it just keeps going in that manner forever. And actually, in the further out you get, the straighter it gets. It's going to start to really follow this asymptote. So it starts off with the same curvature, and then it just kind of follows the asymptote out. So it is really like you just chopped it and opened it out that way and said, go ahead and grow, little dude. Right? But you said, grow along this freaking line here. Okay, so let me give you this worksheet so I can shut up finally.